Okay, so this is test 3. I'm sorry, test 4 review, part 2. I'm not French. Okay. Induction. Here we go. So we have this region. All right, here's a region. And it's got some height and width and whatever. We could call this the width, and we could call this the length. Right? And if you multiply the length times the width, you get the area. So good, this thing has some area, and we can give it a B field. We can have the B field come screaming in through our area. Like so. And our area has a normal to it. Okay, so let's draw the normal to the area. And the normal has an angle between it and the B field. That's the angle. So there's a couple of different ways to do this. You could draw your angle like this, however you want. And I'm not liking this one. It's not perpendicular to the rest of them. So we don't like you. Let's go perpendicular. That's better. Okay, so all the B fields going through, great. We know what that angle is, awesome. And now we can do a thing where we talk about the flux. All right, flux is just flux of anything, but this happens to be the flux of B field going through a certain area. So the B field times the area, all right, but we also need the cosine of the angle between them. So that gives us our total flux. If the angle was 0 degrees, meaning that the area, the normal to the area and the B field were exactly in line with each other, they were parallel to each other, then we'd have the flux is all of the B field times all of the area times our cosine. But in our situation, the B field is going askew to the area, and so then we have to add in this cosine of theta. Okay, so that's easy to figure out, okay? Now, you can have an initial flux and a final flux. All right, and finding delta flux is just whatever the initial flux is minus the final flux. Okay, so that's delta flux. So what is our initial flux? Well, there's a couple of things that could happen. We could have the B field initially times some constant area times some constant cosine of the angle. But we could have an initial, we could say or. In fact, I want to get rid of this. Okay, that didn't take long. Okay, we could have initial, be because the B field is staying constant and the angle is staying constant, but the area is changing. So this would be the original area. And then our third one, so this is all ways that you could have an initial I naught, okay? We could have that the B field stays constant, the area stays constant, but the angle changes. So we would be cosine of theta naught. Okay, so those are three ways. And what could our three phi finals be? Well, this one and this one are linked. So that would mean that we have a B final times an area times the cosine of theta. This one and this one are linked, and that would be A final times a constant B times a constant cosine of theta. And then we have our final flux that's linked to the cosine changing, so we'd have our B, A that are staying the same, but our cosine of theta final. And those two are linked. So now there are three different ways, right? So delta phi, our delta flux, could be equal to our first case. So our first case is A cosine theta, B final minus B initial. Delta phi, delta flux, could be our B times cosine, our B field times cosine times A final minus A initial. And then lastly, we could have our B field times the area, and then we would be doing times the cosine of theta final minus the cosine of theta initial. So those are three ways to do that. Of course, I'm going to go to the next step. All right. So our next step is, what is the EMF that comes about as a result of this magnetic flux? So our EMF is minus N, we'll talk about that in a second, times delta phi, which we just figured out how to get, and then delta time. All right, well, delta time, you can't go wrong there, right? So delta time is just T final minus T initial, and often T initial is 0, so it just really equals T final, right? Because you're starting at T0, and that's fine. So what are we dealing with? We're dealing with a loop. So let's say this is our area, but we've got many loops. So we've got this, and by the way, these are just wires, okay? Why are there two R's? Nobody knows, really. Okay, so these are just wires, and they constitute a loop, all right? And I have current flowing through the loop. I don't know if that's the way the current's going to flow. It could go that direction. It could go this direction. Nobody knows yet. We haven't figured it out. We have to put down some circumstances, okay? So our EMF could be driving the current that way. It could be driving the current the other way. It doesn't matter, but these are wires. Now there could be N of these loops. So when it gets there, it goes down to the next loop. Okay. And then it goes from there down to the next loop. All right, so there could be multiple n loops. Okay, so if we have n of these things, then we're going to get an EMF that is n times this. Okay, because that's what we start with originally. Each of them has some area A, and each of them has a flux of a B field going through them. So let's see if we can draw a B field that goes through all of these things. Okay, so there's our B field going through all the areas, and then we can draw the normal to the areas. I don't know, something like this. And so then it's obvious. I'm such a good drawer. That's our normal. It's obvious what the angle is between these things. That's it. Okay, that's theta. Okay. So, everything's known, right? This has to be a known. It's just a number of loops. So what is our EMF? Here's the key. You get the EMF magnitude. So you don't worry about this negative sign, okay? Just don't even think about it. You go through and you say, okay, how many loops do I have? What's my delta phi? I already figured that out. What's the amount of time that took? We do. And the EMF we can find. Okay, so we find some EMF. Great. Now, what direction is the EMF driving our current? This is where we say, okay, Lenz's law has to happen. All right, so let's scroll down just a little bit and talk about different cases. All right, in the case that I've drawn, nothing is changing except for this B field. So essentially, I have to have an original B field and a final B field sometime later. All right, so we have an original and a final, and all it does is get stronger and weaker, or weaker and stronger, however you want to think about it. But that's going to be our B. Okay, if that's the B and we have a B final, we can do it two different ways. We could say that B final is greater than B initial, or B final is less than B initial. So we're gonna do this both cases, okay? Let's scroll up. And we're gonna figure out the direction for the current in the wires, okay? Due to this B final and B initial, whether they're bigger or smaller than the other one. All right, so let's do case number 1 first. This is case number 1. This is case number 2. And case number 1, easy peasy. Delta phi is A cosine theta. We don't care really about that. But B final and B initial are there. This ends up being a positive thing, okay? And that means that B, our B field, is increasing in this direction, okay? This is an increase. since it's increasing, the B field that gets created by this new EMF, this is our new EMF right here. The B field that gets created by that has to oppose this increase. Okay? We have an induced EMF. So that induced EMF is one that opposes this increase. So what happens? If it's opposing the increase, then that means that the B field that gets created is actually going to be going in the opposite direction. Okay? So this is our induced B field. B induced. All right? For that to happen, what do we have to have the current B to induce that B field? Well, the current, you put your thumb along the current and it goes in the direction of the B field. So that means that our current has to be going in this direction. So you take your thumb, you put it along the current, and then it curls up and makes a B field like this, okay, inside the area. So it's fighting, it's opposing the increase in the B field. All right, so that generates an EMF that has to be pointing in this direction. I want a black EMF here. Okay, that's EMF for the plus. Well, it's simple. If that's the EMF for the plus, then if the cosine is negative, if the B naught is bigger than the B final, this is case number 2. So this is case 1, this is case number 2. There's only one other option, right? It has to be less. It has to go the other direction. So these are I plus and EMF plus, and of course EMF minus goes that way, or case 2, however you want to think about it. And our current also goes in that direction. Goes around the corner here. Okay? So that's it. That's how you do induced. So you don't care about the negative sign. We just figure out the net, the total EMF, the magnitude of it. Then once we have the magnitude, we can go back through, figure out if it's going positive or negative after the fact. Okay. What did we use to figure that out? We used Lenz's law. All right, so Lenz's law helped us figure it out. Back EMF. Let's do a little back EMF. This is due to Lenz's law, and it happens in generators because generators are generating the current. I want to erase just a little bit here. And we'll come down. What is a generator doing? A generator is sitting in a B field. So we've got some B field, typically provided by a magnet. And then this thing is spinning around in a B field because we've got, so it's a generator. We're generating current in this thing. So how do we generate current? We actually take this and hook it up to an axis. Oh, I don't want that. I want black. We have an axis of rotation where this might be all mounted on a piece of wood. Okay, so our wires come off. It's all mounted on a piece of wood. The wood is hooked up to some water wheel or who knows what. Let's call it a water wheel. And water is spinning over this water wheel and causing it to turn. So let's put some water's blue, right? So let's put water running this direction over the wheel, causing the wheel to spin. So it's going in this direction. So that's causing the wheel to spin. That causes our little loop to spin inside this B field, and that generates a current, okay? Because we're just generating a current. That's what we want to do. Now that current has to be split, right? If you watch the other video, which I hope you have, you note that we cut this thing up. And we have two loops, two semicircles, and there's brushes that touch these things. And so when one side, the current basically, this thing does circles, but we don't want the current to flow backwards. We want it to go forward every single time. So we hook it up to these brushes, to these things that are spinning along with the wood, and the current then only goes through one side. So basically our current looks like this. Our current goes positive, and then goes positive, and then goes positive again. So these guys right here with the slit, they basically rectify the voltage EMF and the current. So back EMF, okay, because this thing is doing this change, it genuinely wants to create a current that goes backwards if we're using it I don't okay, look, let me just be honest with you. The test isn't going to make you do all this. The test is going to say something like, why do you get back EMF? And you're going to say Lenz's law. Okay? And when does it happen? It happens in generators. Okay? Generators cause Lenz's law to give us a back EMF. And it's an EMF that opposes the original main EMF that you're trying to drive. and there's nothing you can do about it. It's gonna eat up some of your energy, and that's why motors and generators aren't 100% efficient. Okay, they're 98% efficient. All right, so that's the takeaway there. All right, back EMF. I'm not going to have you try and calculate it. I'm not going to have you try and explain it. I'm going to have you know that it comes from Lenz's law and it happens in generators. Motors are the opposite of generators. It's the same mechanism. Okay, the same mechanism. It's just that the motor takes this and makes your car wheels move. Okay, and then a generator takes this and makes current because it's moving in a constant B field. So that's it. Let's not go into that any further. That's as good as it gets. All right. So we talked about the three different ways. You can have the B field change, and then that gives you a flux change where your area and your cosine of the angle are changing. Okay. You can have the second one where your area is changing. This, by the way, motors and generators, is the theta is changing. Okay, that's theta. B field stays constant, area of the loop stays constant, but this changes. That's probably something you might want to know. Your phi here, if the A changes, well, your B is constant, your cosine of theta is constant, but your area final and your area initial are different. Then the third way is theta is changing. And if theta is changing, then your B field stays constant, your area stays constant, and we're just subtracting the cosine of theta final minus the cosine of theta initial. Okay, now there are names, okay, and these two come about because there's motion involved. How does your area change? Your area can only change if this bar is sliding. Okay, so that bar might have a velocity, and then your area is going from small and it's getting bigger. Okay, or the area could be getting smaller. Okay, because initially it was bigger and now it's got a final and it's not as big as it used to be. So these are called motional EMF. Okay, motional. Not emotional, motional. So motional EMF, all right? Both of these. Okay, that leads us to the transformer equation. And hopefully you guys got enough of the transformer to understand what we're dealing with in a transformer. And in a transformer, we have windings, and there are windings. This thing comes in, goes around, and we'll have some number of windings on this side, and then we'll have another set of windings on this side that might be less, okay? So our N I for the windings. Do we want to call it N1? We could call this N2. We also have another, this could be the primary, and this is your secondary. However you want to think about it. You've got an in, you could call it in, and you could call it out. It all, however you want to do this, okay? But here's our current, all right? So we'll have some current going in and some current going out. On this side, we have some current going in and some current going out. And that's how a transformer works. So what are the transformer equations? Well, your voltage, I don't want green anymore. Your voltage out divided by the voltage in is equal to the number out of windings versus the number of windings going in. Okay, so loops, right? Around this iron stuff, okay? Iron stuff happening. So Vs over Vp equals Ns over Np. That's how the book does it. It doesn't matter however you want to do it. You could have V1 over V2 equals N1 over N2. And this is just flipped, okay? Doesn't matter. The ratios, you can have them positive, negative, whatever. But you can easily solve this for whatever one you want. Okay, so if you want to solve for N2, then you're going to take V2 and divide by V1 and multiply by N1. All right, and so on and so forth. So these are the main transformer equations. This is the same equation. I just wrote it in terms of the different V's and N's, okay? Now, you can use V equals IR to come up with the equation for I and N, because your resistance is going to be the same, okay? So your I is equal to V over R. And now we can substitute in VI, all right? So V1 is equal to I1 times R. And then we're going to divide that by V2, which is equal to I2 times R. The R's cancel. And we're going to note that that is I1 over I2. But that also equals N1 over N2. I don't like that. That doesn't jive. That doesn't jive. Why doesn't that work? V equals IR. This is I1, this is I2. How come I'm doing this wrong? Is that right? Why does that not seem right? I have to go back in my notes here for a second. I don't think that's correct. Where's my... Where's my transformer stuff? Oh, it's because I was using... Yeah. Okay, good. I'm so glad I stopped. Let's do a little erasing here. Forget about all that. That isn't correct. We are not going to do that. We're going to go back to this. Okay, let's do this again. Sorry, everyone. Maybe I'll do a little editing. Our power in, okay, that is equal to our current in times our voltage in. And our power out is equal to our current out and our voltage out. That's better. Oh, God. Okay. If power in is equal to the power out, which it is, then that means that I in is equal to V, not that. Big, I need to do some big erasing and then get back down to small drawing. I in V in is equal to I out V out. And now we can solve V in over V out. All right, and that equals I out over I in. Much better. Oh, God. Okay. So if that's the case, then we can flip this whole thing and use this equation, and we just flip it. Nope, not you. So then what do we get? We get that V out is over V in is equal to N out over N in, but that's also equal to I in over I out. And this is what I was trying to get you guys to see. All right. Now, whether you call it in and out or secondary and primary, however you want, so you can just rewrite it as secondary, primary, I primary, I secondary. Okay, these are equivalent things. 1 and 2, all those, you can just switch them and mix them up. But that's the I equation, and we get that because the power going in is the power going out. I can't do it with V equals IR. Why can't I do it with V equals IR? Because your voltages change. Your voltages in and your voltages out change. Your resistance is in, your resistance is out change. This does not allow us to, we can't do it. You can't use V equals IR. And I had forgotten that. I can't remember everything. What? You guys want me to remember everything? Okay. So that's it. That's for transformers. Let's move upward and onward. Electromagnetic waves. X equals VT. All right? So that gives us lambda, that's our distance, the wavelength, is equal to C, and our time is 1 over the frequency. For 1 lambda, it's the period. It's the period of 1 frequency. So basically time for 1 lambda is equal to our period. And the period is equal to 1 over the frequency. So that's why I said C over F. So now F lambda equals C. And if lambda goes up, F has to go down and vice versa. Because C is not changing. All right, that's the constant. That's why we keep it there. Another thing to know about C is that it's equal to 1 over mu naught epsilon naught, square root. It's a terrible way to do it. I'm sure your instructors in math are going to be upset if I don't do something like this. But who wants to do this? Nobody wants to plug that into their calculator. Gross. You want to use this, plug that into your calculator instead. All right. A nice thing to remember is that the E field is perpendicular to the B field. Okay? So I'm going to draw my E field up and down. That's my E field. I'm going to draw my B field. Has to be perpendicular. 90 degrees. Okay? Has to be. So that's what we're going to go off of. All right, perpendicular things. Okay. Photons. Come on up. Come on down. All right. Photons. Gamma is a photon. It's the symbol for a photon. Photons are wave packets, and they have the two fields, one going like this, and one going like this. We talked about the size differences between them. And we can do it again because a very, very important equation is E. Do I want? I don't want. I want black. This is very important. The E field divided by the B field is equal to C. That means that the E field has to be much larger than the B field because the B field needs this huge number multiplied to it to equal the C. Okay? And we know that C is equal to 3 times 10 to the 8 meters per second. So our B field has to have a lot multiplied by it to give you an E field. That means the B field is a lot smaller than the E field. Okay, it's just a smaller thing. There's no way around it. Okay. It's also secondary, right? You can think of the B field as a secondary field, and it's one of the reasons why we can go back and forth and use motors and generators. It's a great, I mean, we are really, really lucky that we have the ability to do these things. So what do? We go through and we want to figure out our intensity. So even though I'm using the symbol I, I'm really talking about intensity at this point, okay? And we want to talk about the intensity average. And our intensity average is C times epsilon naught over 2 times our maximum E field squared. What are the units? Watts per meter squared. Okay, because intensity is watts per meter squared. That's the units of intensity. All right, so it equals a few things, right? There are different ways to do this, and it's all because this equation and this equation. These two equations combine to make sure that we have all of this all three of these equations. And you can prove up to yourself if you want to play around. You can go through and substitute in these different things and show that the intensity is equal to each of these. It's not hard. You just have to take one of them, like take this one for example, and then just start substituting in C and B or E or whatever and get what you want. Now the maximum, sometimes somebody will say, okay, well, what's the maximum or the peak intensity? Well, that's simply 2 times your average intensity. And if we're multiplying 2 times the average, you can just figure this and then don't divide by 2. Okay, and then you have the peak. So, right, do that, don't do that, whatever. That's on you guys. You can do that easily, I assume. So that pretty much sums it up. Everything, you got to watch some of the other videos. I know because I know I didn't talk about these things in class. But you'll want to read and watch the videos because I definitely explained back EMF. Okay, you want to go through and learn about back EMF You want to go through and learn about Lenz's law. Make sure you know Lenz's law. Transformers I do pretty well. Yeah, it's chapter 19, I believe. No, I'm sorry. 23.6. So there's videos for chapter 23, and that should solve all of that. Okay, good luck on the test, and we'll see you soon.